So this is kind of an interesting question that if you're in my year 8 or 9 class, you'll certainly recognize. And if you weren't, if you're just someone who is not in my actual classes, you might just want to have a go at it because it's kind of a cool problem and kind of interesting. Find all triples of numbers A, B, and C that have an HCF of this and LCM of this. Now, the way that we started doing this in class is we thought about a triple Venn diagram because, of course, we were doing the Venn diagram method for these two things. And we were just trying to fill this in backwards, right? So an HCF of 35, well, this area is the HCF. So therefore, we need to put a 5 and a 7 in here because that makes 35. And now, if we break down 4, 3, 4C, these are all the primes. You can do a decomposition tree if you want to. 5 and 7 are already in the diagram. So we don't need to put those in again. We just need to put in two 2s and a 31. So we just need to throw these into this diagram, and then everything should be fine, except we're not allowed to put them in the middle because then we would mess up the HCF. So okay, maybe the really obvious way to do it is just put two 2s and a 31 all in this section over here. And this will totally work. Now, all of the numbers in the diagram multiply to make this, and the center multiplies to make this. So this is totally a valid solution. This circle, if you multiply all the primes inside of it, make actually 4,340. This circle makes 35. This circle makes 35. And so this ends up being really quite a trivial solution, just because, of course, the answers, well, firstly, because two of the answers are the same, but I never said you couldn't do that. And also because these are just the HCF and LCM. But I also said I never said you couldn't do that either. So this is totally a valid solution. But of course, there are lots of solutions, right? Because you could perhaps take this 31 and you could just move it into this circle and create kind of this solution, which is different, right? Because the 31 is now part of this number. So okay, well, this number is 35 times 4, which is 140. This is 35. And we get a much less trivial solution of these three. And now the question we were kind of working on in class, and if you're not in my class, you can work on now is, can you find literally all of the triples? Like, can you search for them all? Can you play around with these numbers? And also, how many are there and how do you know when you're done? Can you find either some logic that allows you to know that you're done or some very systematic way of looking for these answers such that you know that you've exhausted all possible opportunities when the time comes? Just a couple of hints, though, before you start, I guess. So it goes, we can do this. And we can we're not allowed to put two 2s like this, right? Like it's pretty tempting to say that, okay, well, two 2s and 31 here, then split the 31, now split the 2 down here. But this doesn't work because, of course, the way Venn diagrams work is if you've got a 2 here and a 2 here, they must join in the middle and make it here instead, right? That's how Venn diagrams work. And now you've only got 1 2 in this picture, and so LCM is messed up. You need two 2s. So you'd have to add in another one now, and now this would be a valid solution, which has the answers of this, apparently. So there's a different triple to either of these two. And yeah, so this question is how many ways can you manipulate all of these numbers to find different triples? One more hint before you get going, of course, is just be careful of symmetry. So for example, if two 2s go up here, a 31 here is actually the same solution as this one, because all that's happened is, or that's going to happen, is that these two numbers will be swapped over, right? So there's not complete symmetry here, but there is some symmetry that you do need to be wary of to make sure that you don't double count the same answers that just look a little bit different. So okay, have a go at that, because I'm going to present my working and what I think is the correct answer to how many of these there are in just a second. So the way that I decided to start thinking about this, I essentially just wanted to find a very systematic way of listing these out. And the way that I went about it was, of course, well, we have to put 5 and 7 in the center. But I really thought hard about the 2 extra 2s we need to put in. And I thought about the arrangements to do that. So I thought first, let's just put the two 2s over here. And now all we have to do is think about where the 31 goes. So well, the 31 could go here, right? But it could also go, if the two 2s are there, it could also go here. That's a different place. This is going to create, these are 2 different solutions, right? Because, of course, this circle is different in either one. But, of course, the 31 could instead go into this section over here. Now, this is where we need to be wary of symmetry. Putting the 31 here is the same solution as the first one we've got here by symmetry. And likewise, putting the 31 here would be the same solution as this here because of symmetry. But putting it here is different. And also, of course, putting it up here with the 2s is different. So I think there are 4 ways, and like here, this is just demonstrating. You can check the circles if you want to, but this solution is the same as this solution in terms of the 3 numbers that you get out. So I think there are 4 solutions if you start with the 2s up here. Or really, of course, by symmetry, if you start with the 2s in any of the outsidey bits like this, which I've weirdly described like that. But anyway, I think there are 4 solutions from this starting point. And then, of course, you mess with the 2's. So like we said before, we can't put a 2 here and a 2 here because they would combine. So let's just put a 2 here and a 2 down here. Of course, by symmetry, all of the solutions we're going to get from this would be the same as maybe a 2 here and a 2 here, just by the rotational symmetry that this inherently has. But anyway, now let's think about where to put the 31s again. So we could put the 31 in the middle, up here. We could put it with this 2 over here. That would, of course, be different. We could put it over here. Again, different because it's not with the 2 this time. We could put it over here, which is different. It looks pretty similar to this one that we first had, but it is different, I think. I think it is definitely different, and we can check that by checking out which circle we're going to check out to show that this is different. Is it the 2, 2, 5, 7 circle? Which this one doesn't have. This doesn't have a 2, 2, 5, 7 circle, I don't think. So these two things are different. Just be super careful to check them. You can also put the 31 down here. Again, this is still different to any of these. The only one it could be similar to is this one, but it's not because it's with the 2 this time, which this one wasn't. And finally, you can also put it in with this 2 in here. And so there are actually 6 solutions that come out from the starting point of 2 and 2 here, just counting very systematically. So now we're going to move on to the next place we could put the 2's. So I thought about putting them like this, which is of course different to any of these because it's not in the same circle. This one is not in the same circle as this one, whereas it was here. So again, let's play around with the 31. So it could go there. It could go, of course, down here, which is going to be the same as it going here by symmetry. It could go up here, which is the same as down here by symmetry. So there is a bit more symmetry in this one. And finally, it could go with that 2 in this small area over here. So there are 4 solutions to gain from doing the 2's here. How else could we arrange the 2's? Well, we could actually put them in 2 separate sections like this. Of course, by symmetry, same as doing these 2 or these 2. Again, let's play with the 31. So one could obviously go here. We could put one in with the 2's maybe, or out here. Not quite the same as this one because this one had a 31 and 2 2's in one circle. This one doesn't. It has a 31 and 1 2 in one circle. We could put it over here in the extra space down there. And we could also put it, like I said, with one of the 2's by symmetry. It doesn't matter which one. So there are 4 solutions through that method. And I think we're nearly at the end now. There's one more way to arrange these 2's, and that's to put them both in the same little subsection up here. And now let's think about where the 31 can go. It can obviously go over here. Another arrangement would be to put it by symmetry. It would be the same as over here. But we could put it in one of the, all the way down here maybe, or in one of the smaller sections. And finally, as our last solution, we could put it in with the 2 2's to make this kind of thing here. By symmetry, you can move these around and make it all the same. But I think there are 4 solutions when you put the 2's together like this. And I think that's the only way to do it. So I think we have 4 plus 4 plus 4 plus 4 plus 6 to make 22 solutions in total for triplets of numbers that do this. Of course, if you wanted to add more constraints, like the 3 numbers all have to be distinct, then you might have some more work to do. And I'll encourage anyone to work on that problem and try and narrow down exactly how many there are with triple distinct numbers. You could also put on the extra restriction that you are not allowed to use, that you're not allowed any trivial solutions, I guess, of like repeat 35s or whatever, or repeat I think repeat 35s came up, or repeat numbers at all, which is what I just said, isn't it? The other thing I did want to mention actually was you could also think about maybe this from a combinatorics point of view. Is there a way to count how many solutions there are without actually writing any of them down? Like I exhaustively showed that there are hopefully this many, unless I've made a mistake. But maybe there's some way to, without drawing them down, come up with a very clever, logical way of counting how many there are without actually having to draw anything. So I would welcome any people to do that as well. I think that'd be quite interesting. Anyway, thanks for watching, and I'll see you next time.